Welcome back, everybody, for another Linkfitties deep dive. This time we're going to be tackling multi-agent coordination. Yeah. Basically how all these different things, entities can work together to try to get stuff done, right? And we're going to be drawing mostly from this one research survey that really tries to bring it all together.
Yeah. You know what's really cool about this paper is that it's not just looking at like simple scenarios, like a couple of robots in a room or something. It's really trying to get at like the complexities of how do we coordinate across all these different applications.
Yeah, this is going to be fun. From self-driving cars to, robots in a warehouse or whatever it might be.
Yeah, I love that. We're going to be exploring like the why, the who, and the how of multi-agent coordinations. Like we're going to be able to look behind the scenes. Exactly. And understand all these complex systems, whether it's like a group of people or a network of algorithms or whatever it might be.
Absolutely. And I think the paper does a great job of laying out the groundwork right from the beginning with even defining what is coordination. Okay. And they define it as managing dependencies between activities of different agents because it sounds abstract.
Yeah, it sounds a little abstract, but it's a really powerful concept once you start to kind of unpack it. Yeah? Could you give me some concrete examples to help me wrap my head around it?
Yeah, absolutely. So, let's say you're working on a project as a team, okay, right? Every team member has their own, tasks and responsibilities, but your success depends on everybody else, right? Doing their part and completing their part of the puzzle. And so that interdependence is kind of what we're talking about here, okay? So it's not just about everyone doing their own thing. It's about how those things are it's the connections intertwined.
Yeah, exactly. And how they're managed. Yeah. Why is this so important?
What happens if we don't coordinate properly? I mean, imagine a basketball team, okay, where none of the players ever pass the ball, right? They all just dribble around and do their own thing. They're not going to win many games.
They're not going to win any game, right? No. And then the paper highlights that, in these multi-agent systems, coordination is really key to achieving goals that no single agent could achieve on their own, right? It's about bringing all those strengths together. Yeah, it's about teamwork.
Yeah, exactly. Okay. So we've established that coordination is important, right? But who exactly needs to be coordinating? Is it everyone with everyone all the time? Is it just a free-for-all?
Yeah, well, that's where things get really interesting. The paper dives into this concept of clustering, okay? Which is this idea that, agents that have strong interdependencies, they tend to form these groups, right? Or clusters. So it's kind of like social networks in a way.
Exactly, where, people, birds of a feather flock together. Yes. Okay. So instead of everyone trying to coordinate with everyone else, you have these smaller, more focused groups that are kind of working together based on, their specific tasks or relationships.
Okay. So clustering helps kind of manage the complexity by, it breaks it down, breaking it down into smaller pieces, more manageable pieces. Yeah. So how do these clusters actually form, right? What are the driving forces behind that?
So the paper looks at a bunch of factors. Okay, one is spatial proximity. So if agents are physically close to each other, like robots working in the same part of a factory, they're more likely to form a cluster, right?
Closer together, easier to coordinate.
Exactly. And then you have shared tasks. So, if you have a group of scientists that are all working on the same research project, they need to coordinate. And then there are these higher order relation, like transitive dependencies.
So, for example, if team A relies on team B's output, okay, but team B relies on team C, well, then you might need to bring C into the loop for A and B to coordinate effectively.
I see. So it can be complex. Yeah, it can get pretty complex.
Yeah.
Okay. So those are some really interesting examples.
Yeah.
I'm starting to see how those factors can shape this whole landscape. But now I'm kind of curious about the how, like with all these clusters and dependencies, right?
What are the actual strategies that agents are using to coordinate? It's like a dance.
It must be a complex dance. That's a great way to put it. Yeah. And that's where this paper really shines. It gives this like really amazing overview of all these different methods, okay, that are used for multi-agent coordination. So it's like a toolbox full of it's like a toolbox.
Yeah. Different tools to different situations.
Yeah. Okay. Tell me what's in the toolbox. All right. So one category is what are called rule-based methods. So this is kind of like following a recipe. Okay. Right? Agents are given a set of rules that dictate what they should do based on, certain situations.
Okay? So it's pretty straightforward.
Yeah, it's very simple. Okay, straightforward.
What are the limitations?
But it can be inflexible, right? If something unexpected happens, right? Can't really adapt.
It can't really adapt. So that's where things like game theory come in. So instead of just following these rigid rules, agents actually make strategic decisions, okay, based on what they think other agents are going to do and what the potential outcomes might be. So it's more like a game of chess, okay, where you're thinking ahead and you're trying to anticipate your opponent's moves, right, and plan accordingly, okay? So it's more dynamic.
Yeah, much more dynamic. And then there's this whole other category of learning-based methods, okay? And specifically multi-agent reinforcement learning. And here agents actually learn to coordinate through trial and error.
So instead of being programmed, yeah, there's no programming involved. They're just kind of just learning, figuring it out as they go.
Yeah, figuring it out. Interesting. Okay, and adjusting their behavior based on the feedback that they get.
Okay, that sounds really complex to implement.
It can be, but the potential is huge. Okay, like imagine robots in a warehouse learning to work together better over time, right? Or self-driving cars and adapting to traffic patterns. Yeah, absolutely.
Yeah, that's powerful.
So it's really good for systems that have to operate in these like changing environments, unpredictable environments. Yes, okay. So no matter what method you choose, I imagine there are some common challenges that you have to kind of address in any multi-agent system. Absolutely. So what are some of those key issues?
Yeah, what are the things that like keep researchers up at night? Yeah?
So one of the biggest ones is ensuring what's called system-level performance. So it's not enough for each individual agent to be doing its own thing, right? You want to make sure that the system as a whole system has to work, is achieving its goals, right? And that can be tricky, right? Because they might have competing objectives.
Yeah, totally. Like, how do you reconcile those individual goals, right? How do you get everybody on the same page with the overall objective? It's a tough problem, and there's no, like, easy answer, right? Sometimes it involves compromise. Okay.
Right? Agents kind of have to negotiate and adjust their behavior to reach some kind of outcome that works for everyone. Other times it requires setting up like clear hierarchy or decision processes.
So some agents have more authority.
Yeah, exactly. Okay. So some agents might have more influence than others. So how do you actually design a system that can find that balance, that can achieve that balance, right? Yeah. That's where things get really interesting. The paper talks about, a whole range of approaches, right? From centralized control, where you have like one agent that's calling all the shots, right?
Right.
To decentralized control, where agents are making decisions on their own, right? Based on, local information. So it's kind of like choosing between having a conductor for your orchestra.
Yeah. Versus letting them improvise.
Improvise. Yeah. And it depends on what you're trying to achieve. And it really depends on the application.
Yeah, and the agents that are involved. Okay? This is all really fascinating. We've covered a lot of ground.
I know, right? From the definition of coordination to the methods to the challenges. Yep. I want to see this play out in the real world. I know, me too. Let's get to the applications. All right, so let's dive into some specific applications.
Let's do it. Let's see how this actually works. All right. I'm ready to be amazed.
Get ready, where do we start? So how about we start with something relatable? Okay, you're stuck in traffic.
Okay, I'm familiar with that. Every light is red.
Yes, very familiar. Frustrating. Yeah? So what does this have to do with multi-agent coordination?
How is that related?
Well, traffic management is a classic example of a multi-agent system, okay? Right? Think of each intersection with traffic lights as an intelligent agent, and instead of them all operating in isolation, they communicate with each other, okay? Share information about traffic flow and adjust their timing, okay, to try to optimize the overall system.
So instead of each intersection creating its own little chaos, it's like a symphony of cars moving smoothly through the city. Okay? So the paper goes into some real-world examples of this, showing how these systems can reduce congestion, travel times, even emissions. Okay, it's not just traffic lights, right? We can also think about bringing in self-driving cars into this so they can communicate their positions, speeds, destinations, and even further enhance their efficiency and safety.
Okay, that's a future I can get behind. No more road rage, just smooth sailing all the way to work. Okay, so traffic is just one piece of the puzzle.
Yeah. What other applications kind of caught your eye in this research?
Well, how about we go to robots? Okay, but let's go a little deeper with robots. Okay, imagine a swarm of robots working together in a disaster zone, okay? You know, too dangerous for humans to enter, right? They can coordinate their search patterns, share information about, potential survivors.
Wow. Even work together to clear debris or, provide aid. So it's like having a team of rescuers.
Yeah, tireless rescuers. But that can go where we can't. But I imagine coordinating them in that environment.
Yeah, that's a tough one. It's really challenging.
Yeah, so the paper highlights a couple of approaches. Okay. One is like decentralized control, where each robot is making its own decisions based on its surroundings, but it's still communicating with the rest of the swarm to share information and avoid, doing the same thing twice, right? Other systems use hierarchical control, okay, where you have like a leader robot. Okay, that makes the high decisions, right? And then you have follower robots that execute those tasks.
So it's like having a commander, exactly, and a bunch of, and a team members. Yeah. Okay? So you have that combination of like the overall strategy, but also that flexibility to adapt on the ground. Okay? Robots in disaster zones. Check. What else? What other applications?
All right, how about we go from physical robots to the digital world to those large language models we were talking about? LLM, yeah, the LLMs. So it's like assembling a team of experts, right? But all AI experts.
Okay, right. To tackle complex problems, okay. How does that work?
So imagine a team of LMM agents. Okay, each one trained on a different domain like law, medicine, engineering. They can communicate with each other, right? Sharing information and insights to solve problems that need like multiple perspectives. So instead of working in silos, exact break down those silos. They were all these, you bring all that expertise together.
Yeah, you get that synergy, you get the synergy, okay? But I imagine coordinating all those different, minds.
Yeah. How do you get those minds to work together? Yeah. That's one of the key things that people are working on right now, is how do you design these systems? Yeah. Where they can communicate effectively, right? Because they're not human.
Yeah. They don't think like humans. They don't talk like humans. So you have to almost teach them.
You have to teach them how to communicate, how to speak at common language, the common language, right? Okay. Yeah. So people are working on things like shared ontologies, knowledge representation, and even the ability for these agents to learn each other's language. Wow. Okay. So It's not just programming them.
It's not just programming them. It's teaching them. It's teaching them how to learn.
Okay, but beyond communication, yeah? What are some of the other challenges in coordinating LM agents?
Well, one of the big ones is managing conflict. Okay, right, like human experts. Yeah, these agents might have different perspectives. They might disagree.
Yeah, they might disagree. They might have different biases. They might interpret the data differently. Yeah. Yeah. So, how do you design a system, right, where it's not just the loudest voice that wins?
You don't want the loudest voice to win, right? You want the best argument to win, right? So, how do you make sure the system is reaching sound conclusions? That's a great question.
And that's where people are looking at things like weighted voting schemes. Okay? Argumentation frameworks where agents can actually debate with each other. Wow. So it's like a peer review process.
It's like peer review for AI, but for AI. Yeah. So they can present evidence, counter arguments. Yeah. Try to reach a consensus. Okay. LM-based systems for research. My mind is officially blown.
It's pretty wild stuff. Okay. What other applications did this paper highlight?
All right. How about we go from science to something a little bit more down to earth? Okay. Warehouse automation. Okay, so imagine a warehouse where robots aren't just moving boxes around, right? They're coordinating with each other to optimize storage, manage inventory, fulfill orders efficiently.
Okay, so instead of just chaos, you have this like smoothly choreographed ballad of robots working together. Yeah.
Okay, how does that coordination actually happen?
Right. So the paper talks about a bunch of different mechanisms, okay? One is auction-based systems where robots bid on tasks, okay? Based on their capabilities and how close they are to the item that needs to be moved. Interesting. Other systems use distributed optimization where robots share information about their workload, right? And they adjust their actions to try to keep everything balanced. So it's like a free market for robots.
It is like a free market for robots, but instead of competing for money, they're competing for efficiency. Yeah, they're optimizing the whole system. Okay, I love it. Yeah, so what are the challenges though, right? In coordinating these robots in that kind of dynamic, predictable environment.
One of the big ones is just dealing with unexpected events. Okay, right. What if a robot breaks down? Yeah. What if you get a new shipment in that you weren't expecting, right? The system has to be able to adapt to those changes without, everything falling apart.
So how do you build that flexibility in?
That's where things like multi-agent planning come in, online learning. So they can learn on the fly. Okay, adjust their plans.
Adapt, interesting. Okay, more efficient as they go. So warehouse robots, check.
All right, let's step out of the warehouse into the wider world. Okay, how about transportation systems? Okay, right? Think about self-driving cars navigating a busy city. Okay, they can communicate with each other, share information about where they are, how fast they're going, what their intentions are, right? Avoid collisions, optimize traffic flow.
So it's like they're all talking to each other.
Yeah. It's like this network of intelligent vehicles. But that's incredibly complex to coordinate. Yeah, it's super complex, especially when you've got human drivers in the mix.
Yeah, you got to account for those. You got the unpredictable humans, right?
So researchers are working on these sophisticated algorithms, communication protocols, that allow these cars to anticipate. Yeah. React to what humans might do. Yeah, even the crazy things that humans do, So it's not just about following the rules of the road. It's about understanding the nuances of driving, right? Like defensive driving, but for AI.
Yeah, defensive driving for AI. Okay, exactly. So the paper highlights a couple of approaches. Yeah, things like game theory.
Game theory to model those interactions. Yeah, and machine learning.
Machine learning to predict what the humans are going to do, right? Based on past experience. Okay, that's really interesting.
It's cutting edge stuff. So it sounds like we're on the verge of this like transportation revolution where traffic jams are a thing of the past. Yeah, and our commutes are safer, more efficient. That's the dream. Yeah. Okay. So self-driving cars, check.
Check. But that's just one piece. It's just one piece. The paper also talks about other areas of transportation, right? Like air traffic control, logistics delivery, even things like managing big infrastructure projects like bridges and tunnels.
When bridges and tunnels.
Yeah. Okay.
So transportation in general, transportation broad is being impacted by this.
Yeah.
Okay, what other applications did you come across? How about we go from the ground to the sky, okay? Satellite systems, okay? So imagine a whole bunch of satellites, right, working together.
Yeah. Providing global communication coverage, right? Monitoring weather patterns, even conducting scientific observations. So it's like having all these eyes in the sky.
Yeah, eyes in the sky looking down at us, working together, right, to give us this comprehensive view of what's happening, but coordinating all those satellites.
Yeah, that's a tough one. That must be really hard.
That's a tough one. The distances are huge. You need precise timing. Everything has to be perfect.
Everything has to be just right. Yeah.
So the paper talks about all the amazing engineering that goes into these systems. You know, they have to communicate with each other even when they're on opposite sides of the Earth, right? They have to adjust their orbits. Yeah. Their positions to maintain coverage and avoid bumping into each other. It's like a ballot in space.
Yeah, a very delicate ballot. A very delicate ballot. Okay. But what are the benefits? Right. So what do we get out of this? Like, why go through all that trouble?
Well, you get things like seamless global communication, okay? Even in remote areas, you get more accurate weather forecasts, which can help with things like disaster preparedness. Yeah. And you can collect better data about our planet, right? Which leads to new discoveries and better understanding of our world, okay? So it's all about that, your global perspective.
The big picture. Yeah, okay. Satellite systems check. All right. This deep dive has taken us all over the place.
I know, right? Okay, what else? What other applications did you come across? How about we bring it back down to Earth? Okay, literally. Okay, how about smart homes and smart cities? Okay, so imagine a future where your appliances, your car, even the infrastructure of your city are all working together to make your life easier, safer, more efficient. It's like having a personal assistant that can manage everything for your whole life, for your whole world. Okay? But coordinating all those things.
Yeah, that's a big challenge. That must be really hard. Yeah. How do you even approach that?
Right, so that's where this idea of the Internet of Things comes in. Okay, or IT. So the idea is to connect all these devices, right, to a common network so they can talk to each other, share information. Okay, so multi-agent coordination is what manages.
That's the glue. Yeah. It's the glue that holds it all together. The glue that makes sure everything's working smoothly. So instead of each device just doing its own thing, now they can all work together like a team. Yeah, to anticipate your needs, right? Provide personalized services. Okay. So what are some examples of that?
Well, imagine your alarm clock talking to your coffee maker. So you have a fresh cup of coffee when you wake up.
I like that one.
Or your car talking to the traffic management system so you can avoid all the traffic jams.
Okay, so it's not just convenience though.
No, it's not just convenience. It's also things like saving energy, making cities more sustainable, improving safety and security by coordinating all these systems, making our commutes faster and less stressful. So multi-agent coordination is really the key to unlocking all that potential, this connected world. But I imagine there were some concerns.
Oh, yeah, for sure. Right. Especially when it comes to things like privacy and security. Huge concerns.
Yeah, absolutely. Right. As we connect more devices, that creates more vulnerability, points of failure. So how do we address that? That's a big question. So the paper talks about some approaches like using decentralized architectures. where the data is spread out. So it's harder for hackers to get at it. So there's no single point of failure.
Exactly. And people are also working on these privacy-preserving algorithms that allow systems to share information without revealing personal data. So we can get the benefits without sacrificing privacy. Okay, smart homes and smart cities. Check. Okay? We've covered a lot of ground.
We have covered a lot of ground.
Yeah?
But I feel like there's still so much more.
Oh, there's so much more to explore. Yeah? The world of multi-ant coordination is huge. It's constantly changing, and we've just scratched the surface. Okay? But I hope this has given you a taste of this field and all the amazing things that can happen when different entities work together.
It has been fascinating so far. Yeah. But before we get too carried away, I think we should take a step back. Yeah. And look at some of the challenges, the limitations and limitations of this, because it's not all sunshine and roses. It's not a silver bullet. So let's dive into those a little bit.
Yeah, let's get into the nitty-gritty. Okay? All right. So, are we ready to jump into some real-world applications?
Yeah. Let's see how this stuff actually plays out. All right. So we talked about LLM-based system earlier. Exactly. And one of the coolest examples in this paper is using them for scientific research. So imagine you have a group of these LLM agents, each one specializing in a different scientific discipline, and they're working together to analyze data, generate hypotheses, even design experiments.
So it's like instead of having scientists working in silos, you have this like brain trust.
Yeah.
This mega brain of AI working on these problems.
Yeah.
And the paper even talks about how these LLM agents could automate parts of the research process. So human researchers can focus on the big picture stuff, right? So it's not about replacing scientists. It's about augmenting them, giving them more tools.
Yeah. Giving them superpowers. I like it, okay? But I imagine there are some challenges.
Oh yeah, for sure. In coordinating these LM agents, they're not human. They don't think like us. So what are some of those challenges? Well, one of the big ones is communication. LMs are great at processing language, but they still struggle with things like context.
Okay? Ambiguity, interpreting data from different fields. Yeah? It's like trying to get people who speak different languages to collaborate.
Exactly, it's a language barrier.
Yeah. Okay.
So researchers are working on new techniques to overcome that. Okay. Things like shared ontologies, knowledge representation. Okay. Even teaching these agents to learn each other's language over time. So it's not just about giving them knowledge. It's about teaching them how to communicate, how to talk to each other.
Yeah. Okay, that's fascinating. But communication is just one piece of the puzzle. Another big challenge is managing conflict. Okay, just like human experts, these LM agents might have different perspectives.
Yeah, they might disagree.
Yeah, they might disagree. They might interpret the data differently. Yeah, so how do you make sure the system is reaching the right conclusions? So you don't want just the loudest voice to win. You want the best argument to win. So people are looking at things like weighted voting systems. Okay? Argumentation frameworks where these agents can actually debate with each other.
Wow. So it's like AI peer review. It is like AI peer review. They present evidence, they make counter-arguments, and they try to reach a consensus.
Okay, LLM agents for scientific research. Yeah, it's pretty wild stuff. It is pretty wild. Okay, let's move on to a different application. Okay, how about we go from science to something a little bit more practical? Okay, warehouse automation. Okay, robots in a warehouse, but not just moving boxes around. They're actually coordinating with each other to optimize storage, manage inventory, fulfill orders. So instead of just having chaos, you have this like smoothly running system where every robot knows what it's doing and they're all working together.
Okay, so how does that actually work? Right? So the paper dives into a bunch of different mechanisms like auction-based systems. where robots bid on tasks based on their capabilities and their location.
Interesting.
And then you have distributed optimization, okay, where robots share information about their workload, okay? And they adjust their actions to try to balance everything out, okay? So it's kind of like a free market for robots.
It is like a free market, but instead of money, it's efficiency. Yeah, they're optimizing for the greater good. I love it. Yeah. But there are challenges, of course, right? What are some of the challenges in coordinating robots in a warehouse? Well, one of the big ones is unexpected events. What happens if a robot breaks down or you get a new shipment that you weren't expecting? Yeah, the system has to be able to adapt.
Adapt on the fly, right? So that's where techniques like multi-agent planning and online learning come in so they can adjust their plans.
Yeah, they can learn from their experiences, learn as they go, exactly, and become more efficient over time. Okay? So, warehouse robots, check. What else?
All right, let's step out of the warehouse and into the world of transportation. Okay, how about self-driving cars? Okay, we touched on this a little bit.
Yeah, we did, but let's dive a little deeper. Okay, so imagine self-driving cars navigating a busy city. Okay, they can communicate with each other, share information about their position, speed, and tensions to avoid collisions, and make traffic flow more smoothly.
So it's like having a network of cars that are all talking to each other. Yeah, exactly. Creating this kind of collective intelligence on the road. But that sounds incredibly complex.
It is incredibly complex, especially when you have human drivers in the mix. You got to account for the unpredictability.
The unpredictability of humans. Researchers are developing these really sophisticated algorithms, communication protocols to help these cars anticipate and react to what other drivers are doing. So it's not just about following the rules of the road.
No, it's about understanding the nuances of driving, like how to handle a merge or how to anticipate what a pedestrian might do. Okay. So, it's like defensive driving.
Yeah, defensive driving, but for AI. Okay. And the paper talks about some interesting approaches like using game theory to model the interactions between cars. Okay. Or using machine learning to actually predict what human drivers might do based on their past behavior.
Yeah, based on their past behavior. Okay. That's amazing. Yeah, it's really cutting edge stuff. It sounds like we're on the verge of this transportation revolution. I think we are where traffic jams are a thing of the past. No more traffic jams, no more road rage, just smooth sailing, yeah? Okay? Self-driving cars, check. But that's just one piece of the puzzle. The paper also talks about other areas of transportation, like air traffic control, logistics, delivery. Yeah. Even managing big infrastructure projects. Okay? So, transportation in general.
Broadly.
Okay? What other applications did you find?
All right. Let's go from the ground to the sky. Okay. Satellite systems. Imagine a whole bunch of satellites working together up in space, providing global communication coverage, monitoring weather patterns. Okay. Conducting scientific observations. It's like having all these eyes in the sky.
Yeah. Eyes in the sky looking down on us. Yeah. Giving us this global perspective. But coordinating all those satellites must be incredibly challenging.
These incredibly challenging. The distances are vast, huge distances. You need precise timing. Yeah, everything has to be just right. So, how do they do it? Right? Well, the paper talks about all the amazing engineering that goes into these systems. They have to communicate with each other even when they're on opposite sides of the planet. They have to adjust their orbits and positions to maintain coverage and avoid collisions, like a bollet in space.
Okay. So, what are the benefits of all that? Why go through all that trouble? Yeah. Well, you get things like seamless global communication, even in remote areas. You get more accurate weather forecasts, which can help with disaster preparedness. You can collect better data about our planet, leading to new discoveries and a better understanding of how things work. So, it's all about that global view. Yeah, that big picture perspective. Okay? Satellite systems check. All right? This deep dive is really taking us all over the place. What else? What other applications did you find?
All right, how about we bring it back down to Earth? Okay, literally. Okay, smart homes and smart cities. Okay, so imagine a future where your appliances, your car, even the infrastructure of your city are all working together to make your life easier, safer, more efficient. It's like having a personal assistant for your entire life.
Yeah, your whole world is working together. But coordinating all those different systems, yeah, that's a huge undertaking. How do you even begin to approach that?
Right. So that's where this idea of the Internet of Things comes in, the IoT, connecting all these devices to a common network so they can talk to each other, share information, and multi-ant coordination is the glue that holds it all together.
It's the brains of the operation. The brains of the operation making sure everything's working smoothly. So instead of each device just doing its own thing, now they're all working as a team.
Yeah, a well-oiled machine.
Okay, so give me some examples, all right? So imagine your alarm clock talking to your coffee maker, okay? So you have a fresh cup of coffee when you wake up. I like that one. Or your car talking to the traffic management system, so you can avoid traffic jams on your way to work, okay? But it's not just about convenience, though.
No, it's not just convenience. It's also things like saving energy, okay? Making cities more sustainable, improving safety and security, yeah, by coordinating all these different systems. So multi-agent coordination is really the key to unlocking all that potential of this connected world. But I imagine there were some concerns.
Oh, yeah, for sure. Especially when it comes to things like privacy and security. Huge concerns, because as we connect more devices, we create more vulnerabilities, more points of failure.
How do we address those concerns, right? Well, the paper talks about a few approaches like using decentralized architectures, okay, where the data is spread out so it's harder for hackers to get to it. So there's no single point of failure. Exactly. Right. And people are also working on privacy-preserving algorithm that allows systems to share information without revealing personal data so we can get the benefits without sacrificing our privacy.
Okay. Smart homes and smart cities. Check. Wow. We've covered a lot of ground. We have covered a lot of ground. This deep dive is really taking us all over the place. I know. I told you it was going to be a wild ride. But I feel like there's still so much more to explore. Oh, there's so much more. The world of multi-coordination is vast and constantly evolving. Yeah, it's a rapidly developing field. Yeah, we've just scratched the surface here. But I hope this has given you a taste of what's possible, yeah. All the amazing things that can happen when different entities work together, when we all work together. Yeah, okay. But before we get too carried away, we should take a step back. Yeah, and look at some of the challenges and limitations, the downsides, the multi-ant coordination. Yeah, because it's not a silver bullet. There are some real-world considerations. So let's dive into those a little bit. All right, let's get into nitty-gritty. So we've seen all these amazing things that multi-agent coordination can do. Yeah. But like you were saying, it's not easy, smooth sailing. So what are some of the things that make it hard to get these systems to work perfectly? Right. So one of the biggest challenges is just the sheer complexity of these systems. You know, as the number of agents grows and the interactions between them get more complicated, it can be really hard to design and manage them effectively. It's like juggling a dozen balls at once.
Yeah, exactly. Something's bound to drop. At some point, you just can't keep track of everything. And in these systems, a drop ball could be a real problem.
Oh, yeah, absolutely. Right? Like in the self-driving car system. Yeah, a miscommunication could lead to an accident or a power outage on the grid. Yeah, the stakes are high. The stakes are really high. So, how are researchers addressing this complexity challenge?
Right. So it's a tough problem, but people are developing new tools and techniques to make it more manageable, like formal verification methods where you mathematically prove that the system is going to work correctly. So you're trying to eliminate those errors before they happen. Exactly. You want to catch those drop balls before they hit the ground. Yeah, okay. And there are also new programming languages and software frameworks specifically for building these multi-ant systems. So it's becoming easier to actually create these systems.
Yeah, it's getting easier to build and test these complex systems. Okay, that's good news. It is, but what about scalability? You know, we talked about systems with hundreds, thousands, even millions of agents. Yeah. How do you handle that? How do you make sure a system like that doesn't just collapse under its own weight? Right? So scalability is a huge challenge. As the number of agents increases, all the communication, the computation, the potential for conflicts, it all just explodes. It's like trying to organize a party for 1,000 people.
Yeah, it's a logistical nightmare.
Yeah. So how do you design a system that can handle that? So one approach is to use decentralized architectures where agents are organized into smaller groups. So you don't need everyone talking to everyone else all the time. So you're breaking that giant party down into smaller, more manageable groups. Okay? But even with smaller groups, don't you still need some level of central control?
Absolutely. And that's where hierarchical control comes in. Okay, so you have higher level agents that set the overall goals, and then lower level agents handle the details of carrying out those goals. So it's like a military, you have the generals, and then you have the soldiers. Exactly. You need both. Okay, so it's about finding the right balance between centralized and decentralized control. Yeah. It depends on the application. Okay. But beyond architecture, are there other considerations for scalability?
Oh yeah, communication is a big one. Okay? As the number of agents grows, the amount of data they need to exchange can just overwhelm the system. It's like trying to have a conversation in a crowded room.
Yeah, exactly. Everyone's talking over each other. Nobody can hear anything. You can't get a word in edgewise.
How do you solve that, right? So researchers are working on more efficient communication protocols, okay? Where agents only share the information that's absolutely necessary. Okay? So they're cutting down on the chatter. Okay, so we've got complexity, scalability, communication. Yeah, those are some big ones. But it sounds like researchers are making progress. They are. What are some other areas where more work needs to be done?
One area that's getting a lot of attention is robustness. Okay, you know, real-world systems are messy, things break down, unexpected events happen, so these systems have to be able to handle that. Yeah, they have to be able to adapt and recover from failures.
Well, it's not just about designing a system that works perfectly in a lab. The real world is a lot more chaotic. Yeah? So, how do you build that kind of resilience into the system?
Right, so that's where research into things like fault tolerance, exception handling, self-healing comes in. So the system can kind of fix itself. Yeah. Ideally, you want a system that can diagnose and repair problems on its own. Okay, and what about security?
Oh, yeah. Security is huge. Because as we connect more and more devices to the internet, that creates more opportunities for attacks, more vulnerability. So these systems need to be designed with security in mind. Absolutely. From the ground up.
From the ground up.
Okay. So what are researchers doing in that area?
So people are working on secure communication protocols. Oh, authentication mechanisms, intrusion detection systems. So it's like building a fortress. Yeah, you need strong defenses to protect the system. And you need to be able to detect and respond to attacks. Okay, so, and security. Two more big challenges.
But I think we're making progress, okay? This has been an incredible journey. It has been a wild ride. We've seen how multi-agent coordination can be used for all sorts of things, from robots to satellites to AI experts. But we've also seen that there are some really tough challenges in making these systems work reliably and safely in the real world. It's a balancing act. But I think this camera does a great job of highlighting both the potential and the pitfalls.
I agree. It's a great roadmap for the future of this field. Yeah, absolutely. But I want to bring it back to our listeners for a second. Okay, why should they care about all of this, right? So why does any of this matter? Yeah. How is this going to impact their lives? So the truth is, multi-agent coordination is ready all around us, even if we don't realize it. Okay, give me some examples. All right, so traffic management systems. Okay, recommendation algorithms. Those are all multi-agent systems. And as this technology gets more advanced, it's going to have an even bigger impact.
Absolutely. Can you paint a picture of what that future might look like?
Yeah. So imagine a world where your smartphone anticipates your needs. Okay? Adjusts the temperature, the letting your music playlist based on your preferences and your routine. That sounds pretty nice. Yeah. Or imagine a healthcare system. Okay. Where robots assist doctors and nurses, providing personalized care, monitoring patients 24/7. Okay. Or a transportation system where self-driving cars and smart traffic lights work together to make our commutes faster, safer, less stressful. Okay? So, it's all about making our lives easier and better, using technology to solve problems and improve the way we live. That's a future I can get behind.
Me too. But it's important to remember that technology is a tool. It's not a magic wand, and it can be used for good or for bad. Absolutely. So, as we develop these increasingly powerful multi-agent systems, we need to think carefully about the ethical implications. We need to make sure they're used responsibly and for the benefit of everyone, for the benefit of humanity. Yeah, it's a conversation that needs to involve everyone. Scientists, engineers, policymakers, ethicists, the public. Yeah, we all have a stake in this. We all have a role to play. That's a great point. So, as we wrap up our deep dive into multi-agent coordination, I encourage our listeners to keep exploring, keep asking questions, keep engaging in this important conversation. Yeah, the future is being shaped right now. It is. And we all have a part in that. Absolutely. Well said. That's a perfect note to end on. Yeah. Thanks for joining us at Linkfity Corporation on this fascinating journey into the world of multi-agent coordination.
My pleasure. Until next time, keep diving deep.